The concrete walls were supposed to be impenetrable, reinforced with steel rebar poured layer by layer, hardened over months of construction. These weren't just buildings. They were fortresses, bunkers designed to withstand anything the enemy could throw at them. Artillery shells would bounce off, bombs would crater the ground around them, but the men inside would remain safe, protected by meters of solid concrete and steel. That was the theory, at least. But in the laboratories and proving grounds of World War II, engineers on both sides were developing something that would turn these concrete sanctuaries into death traps, something that would transform impregnable fortresses into burning metal coffins. Before we dive deeper into this incredible story of innovation and destruction, I want to ask you to hit that like button and subscribe to the channel. Your support helps us bring you more fascinating stories from history. And please leave a comment below telling us what other topics from World War II you'd like us to explore. Now let's continue with our story. The year is 1940, the Battle of France is reaching its conclusion, and German forces are encountering something that gives even their most experienced commanders pause. The Maginot Line, France's vast network of underground fortresses, stretches along the Franco-German border like a concrete serpent. Each fortification is a marvel of military engineering. Some bunkers have walls 5 meters thick. Artillery casemates are protected by reinforced concrete that could stop any conventional shell in existence. The French had spent billions of francs and more than a decade building what they believed was an impenetrable wall. Web or Kisiu. The German army brought their most powerful weapons to bear against these fortifications. The 88mm anti-aircraft gun, already proving its worth against tanks, was turned on bunker walls. Heavy artillery pieces lobbed shells weighing hundreds of pounds. But the results were disappointing. Shells would impact the concrete, creating impressive explosions and clouds of dust. But when the smoke cleared, the bunkers remained largely intact. Perhaps there would be a crater, some spalling on the exterior, but the structure itself held firm. The men inside were shaken but alive, ready to continue fighting. This presented a serious problem for military planners. Modern warfare was becoming increasingly dependent on fortified positions. Not just massive fortress complexes like the Maginot Line, but smaller bunkers, pillboxes, and concrete reinforced structures that could control key terrain. Machine gun nests encased in concrete could hold up entire divisions. Artillery observation posts with reinforced roofs could direct fire with impunity. Coastal batteries protected by meters of concrete could dominate sea approaches. If armies couldn't defeat these fortifications efficiently, warfare would bog down into the static trench battles of World War I all over again. The challenge was fundamentally one of physics. Concrete is remarkably good at dissipating force. When a conventional high-explosive shell hits a concrete wall, most of the explosive energy radiates outward in all directions. Some of it creates a crater. Some of it becomes heat and light, but very little of it actually penetrates deeply into the structure. The reinforcing steel bars embedded in the concrete help distribute the shock, preventing catastrophic failure. Even armor-piercing shells, designed to punch through steel tank armor, weren't ideal. They relied on kinetic energy and a very hard penetrating tip, but concrete's granular structure would cause them to tumble or shatter. What was needed was something entirely different, a weapon that could focus its energy into a narrow, intense point, something that could burn through concrete like a blowtorch through wood. And in laboratories across Germany, Britain, the Soviet Union, and eventually the United States, scientists and engineers were racing to develop exactly that. Web. The story of bunker-busting technology in World War II is actually two parallel stories. The first involves aircraft dropping massive bombs from high altitude. The second, which is our main focus today, involves artillery shells that could be fired from conventional guns. Let's start with the aerial bombs, because they help us understand the principles that would later be applied to shells. British engineer Barnes Wallis became obsessed with the problem of destroying hardened targets. He had already gained fame for designing the bouncing bomb used in the famous Dambusters raid, but he knew that weapon wouldn't work against concrete fortifications. Wallis approached the problem from a geologist's perspective. He realized that trying to blast through meters of concrete with brute force was inefficient. Instead, what if you could create an earthquake? Web Kino. The result was the Tallboy bomb and later its bigger brother, the Grand Slam. These weren't conventional bombs. They were streamlined, aerodynamic penetrators weighing 12,000 pounds and 22,000 pounds, respectively. Made from a single casting of high-tensile steel, they were designed to be dropped from extreme altitude. As they fell, they accelerated to speeds approaching the speed of sound, over 750 miles per hour. The bombs weren't trying to explode on the surface. Instead, they were designed to penetrate deep into the earth or through concrete roofs, then detonate underground. Web Yanti Web Hyunt. When a tall boy or Grand Slam detonated deep underground or inside a bunker, it created what Wallis called an earthquake effect. The explosive energy couldn't dissipate into the air. Instead, it transferred into the surrounding earth and concrete as a massive shock wave. This shock wave caused catastrophic structural damage throughout the entire target. Walls would crack, floors would collapse, and the structure would literally tear itself apart from the inside. In tests against reinforced concrete, these bombs could penetrate over 15 feet of hardened concrete before detonating. Webaust. But bombs had limitations. You needed aircraft, you needed to get them through enemy air defenses, and you needed favorable weather conditions. What if you could achieve similar effects with artillery that could be positioned on the ground and fire repeatedly? This is where our story gets truly fascinating, because it leads us to one of the most secret weapons of World War II, a shell so classified that the Germans were terrified of firing it in case a dud fell into Allied hands. Web Aspiantanir. Web Korsto. In Germany, an engineer named August Konders was working on a revolutionary concept. He approached the penetration problem from first principles. Why did conventional shells perform so poorly against concrete? Because they presented a blunt surface that had to push through all that material. What if instead you made a shell that was essentially an arrow? Long, thin, with a very small diameter tip, but tremendous mass behind it. This would give it incredible sectional density, the ratio of mass to cross-sectional area. A shell with high sectional density would concentrate all its kinetic energy into a tiny point, Webwertmors. Wabwand. The result was called the Röchling shell, and it looked like nothing else in any army's arsenal. Imagine an enormous dart, over 6 feet long, made from chrome vanadium steel, one of the hardest alloys available. The shell was subcaliber, meaning it was narrower than the bore of the gun firing it. To make it work, engineers attached a discarding flange that acted like a driving band, engaging the rifling of the gun barrel. When the shell left the barrel, this flange would fall away, and the dart would continue to the target. Web 4. The performance of the Röchling shell was absolutely extraordinary. In tests conducted between 1942 and 1943, these shells demonstrated the ability to penetrate more than 4 meters over 13 feet of reinforced concrete. Read that again. 13 feet. That's more concrete than the roof of almost any bunker built during World War II. The shell would punch through the roof, continue through the floor, and bury itself in the earth beneath the fortification web. Pols. Web. Jaukotor. The Germans tested Richtling shells against real fortifications. Fort de Batisse in Belgium, a modern fortress completed in the 1930s with state-of-the-art concrete protection, was subjected to bombardment. Fort d'Aubin-Neufchâteau, another Belgian fortress, received similar treatment. In Czechoslovakia, the fortresses at Hurka, Hanička, and Dobršov, built along the pre-war border and considered among the strongest in Europe, all faced Richtling shells. The results were terrifying. Shells would pierce roofs that were supposed to be impervious, detonate inside, and turn the underground chambers into scenes of absolute carnage. Web. Ponce. Web. Think about what it would be like to be inside a bunker when a Richtling shell hit. You're deep underground, surrounded by concrete and steel, believing yourself safe. Then there's an impact above, not the usual boom of a shell exploding on the surface, but a different sound. A massive crack like a giant hammer striking stone. Concrete dust begins to fall from the ceiling. Before you can process what's happening, the shell has punched completely through, traveling at enormous velocity. If the shell has a delayed fuse, there might be a few seconds of horrified realization before it detonates. The explosion inside an enclosed concrete space is indescribable. The blast wave has nowhere to go. It reflects off the walls, amplifying in intensity, turning the air itself into a weapon. Web. Yekti web piestikotsti. But the Richtling shell had a fatal flaw, the same flaw that afflicts most sub-caliber penetrators: accuracy. Because the shell was so long and thin, and because it left the barrel at relatively low velocity, it was extremely sensitive to crosswinds and atmospheric conditions. At a range of just 1,000 meters, about 3,000 feet, the dispersion was 36 meters. That's 118 feet. For comparison, a well-trained artillery crew with a conventional shell could expect to land rounds within a few meters of their aim point at that range. With a Richtling shell, you might miss a bunker entirely, even with perfect aim. This accuracy problem meant that Richtling shells were impractical for most combat situations. Despite manufacturing approximately 6,000 shells, only about 200 were ever fired in actual combat. The German High Command classified them as a secret weapon and restricted their use, partly because they didn't want duds falling into Allied hands, but mostly because they simply couldn't hit what they were aiming at with any reliability. Web Piporchau. While the Germans were developing their arrow shell, other nations were pursuing a completely different approach to the bunker problem. Instead of relying purely on kinetic energy, what if you could create a shell that generated its own penetrating jet of superheated metal? This concept would lead to one of the most important weapons innovations of World War II, the shaped charge, Websichernis, Webertrios. The physics behind shaped charges had been understood since the late 19th century. An American scientist named Charles Munro discovered that if you shaped an explosive charge with a hollow cavity, usually a cone, and lined that cavity with metal, something remarkable happened when you detonated it. Instead of the explosive force radiating in all directions, the metal liner would collapse inward and form a jet, a stream of metal particles traveling at speeds that seemed impossible. We're talking about velocities of 8 to 10 kilometers per second, nearly 30 times the speed of sound. Web attend. What makes this jet so devastating is not heat, despite what the acronym HEAT, High Explosive Anti-Tank, might suggest. The metal jet doesn't melt its way through armor or concrete. Instead, it's a purely kinetic phenomenon. The jet is traveling so fast and carrying so much momentum that when it strikes a target, the metal behaves like a liquid, even though X-ray crystallography shows it remains solid. The immense pressure, millions of pounds per square inch, causes the target material to flow out of the way. Imagine a stream of water cutting through sand, except the water is copper, traveling at hypersonic speeds, and the sand is steel or concrete. Web sixpakis. Web tree. Early shaped charge warheads developed during World War II could penetrate armor equivalent to 150 to 250% of their diameter. A shaped charge with a 6-inch diameter could punch through 15 inches of steel armor. This was revolutionary. It meant that a relatively small weapon, something a soldier could carry, could defeat the thickest tank armor in existence. But shaped charges worked against concrete too, and that made them incredibly valuable for attacking fortifications. Web Aspon. The Germans were the first to weaponize shaped charges on a large scale. Their Panzerfaust, a single-shot anti-tank weapon, used a shaped charge warhead and could be operated by infantry. The Panzerschreck, essentially a copy of the American bazooka but with a larger warhead, became feared by Allied tank crews. But these weapons weren't just used against vehicles. In the brutal close quarters fighting in cities like Stalingrad and later Berlin, shaped charge weapons proved devastatingly effective against bunkers and fortified buildings. A soldier could fire a Panzerschreck at a concrete wall, and the shaped charge jet would punch through, often with lethal consequences for anyone inside. Web Kennekempt. The Americans recognized the bunker-busting potential of their bazooka early in the Pacific Campaign. Japanese defensive positions on islands like Tarawa, Iwo Jima, and Okinawa consisted of reinforced concrete pillboxes and bunkers that were nearly impossible to destroy with conventional weapons. Machine gun fire was useless. Hand grenades couldn't penetrate the firing slits. Even direct hits from tank guns often failed to knock out these positions. But a bazooka, firing a shaped charge rocket, could punch through the concrete walls. The jet would penetrate into the interior, and even if it didn't harm anyone directly, the pressure wave and fragments of concrete spalling from the interior walls would cause casualties. Suddenly, American infantry had a weapon that could neutralize these fortifications without calling in airstrikes or naval gunfire. Web Fin. Now, let's talk about what actually happened inside these bunkers when they were hit by penetrating shells or shaped charges, because this is where the story becomes truly nightmarish. Even if a penetrator didn't explode, even if a shaped charge jet didn't directly harm anyone, there was a secondary effect that was arguably more lethal than the primary weapon itself. This effect is called spalling. Web poisson. Spalling occurs when a high-velocity impact on one side of a wall causes material to violently break away from the opposite side. Think of it like this. A shell or shaped charge jet hits the outside of a concrete bunker wall. The impact creates an intense shock wave that travels through the concrete. When this shock wave reaches the interior surface, it reflects back. But concrete is much stronger in compression than in tension. The reflected shock wave, pulling rather than pushing, exceeds the concrete's tensile strength, and chunks of concrete, along with fragments of the steel reinforcing bars, explosively detach from the wall at high velocity. These fragments become deadly projectiles. Pieces of concrete the size of a fist, traveling at hundreds of feet per second, ricochet around the interior of the bunker. Steel reinforcement bar fragments act like shrapnel. The effect is like detonating a fragmentation grenade inside the bunker, except the fragments are heavier and traveling faster. Soldiers could be standing dozens of feet from an impact point and still be struck by spalling. There are accounts from veterans of being inside bunkers during artillery bombardments and having comrades struck down by concrete fragments, even though the bunker itself remained structurally sound. Bunker designers tried to mitigate spalling by adding an inner layer of material to catch fragments. Sometimes this was simply sandbags stacked against the walls. More sophisticated bunkers had an interior lining of wood or even metal plates designed to catch spalling fragments before they could harm personnel. But this added weight, cost, and complexity. Many field fortifications and quickly built bunkers had no spall protection at all. Web. The psychological effect of being in a bunker under fire from penetrating weapons was profound. The whole point of a bunker is to provide psychological comfort as well as physical protection. You're underground, surrounded by concrete and earth, isolated from the chaos of the battlefield. But when shells start penetrating that protection, when chunks of concrete start flying around the interior, that psychological comfort evaporates instantly. You realize that your fortress is actually a trap. The thick walls that were supposed to protect you are now generating the fragments that might harm you. You can't see what's happening outside. You don't know when the next impact will come. And you certainly can't leave because stepping outside is almost certainly more dangerous than staying inside. There's another effect of shaped charges that made them particularly terrifying in confined spaces. Remember that the metal jet is traveling at hypersonic speeds. When it penetrates armor or concrete, it doesn't just make a neat hole. The penetration process is violent and chaotic. The jet is essentially drilling through the material at incredible speed, and this generates tremendous heat. While the jet itself isn't melted when it's formed, the friction and compression of penetration can heat it to temperatures between 800 and 1200 degrees Kelvin, approaching the melting point of copper. When a shaped charge jet penetrates into a confined space like a bunker interior, it brings this heat with it. There are accounts from World War II of shaped charges used against tanks, causing fires inside the fighting compartment. The same thing could happen in bunkers. If the jet struck ammunition or fuel supplies, it could ignite them. Even without igniting stored materials, the jet itself could cause burns. And remember, this is all happening in an enclosed concrete box with limited ventilation. The air rapidly fills with smoke, concrete dust, and possibly toxic fumes from burning materials. Men trying to breathe find themselves choking, unable to see, ears ringing from the overpressure of the initial penetration. This brings us to perhaps the most disturbing aspect of these weapons. A bunker that has been penetrated by multiple shells becomes, in effect, a death trap. The structural integrity is compromised. Cracks spread through the concrete. Water begins to seep in. The ventilation system may be damaged. Exits can become blocked by rubble. And if the enemy knows that the bunker has been damaged, they can continue to bombard it, confident that the defenders have no effective protection. There are documented cases from the Eastern Front of Soviet bunkers that were hit by German artillery using concrete-piercing shells. The initial penetrations would wound or eliminate some of the defenders. The survivors, now aware that their fortification offered little protection, faced a horrible choice. Stay inside and risk being caught in the next barrage, or attempt to evacuate through exits that might be covered by enemy fire. Many chose to stay. Over hours or days of continued bombardment, the bunker would be gradually demolished from the inside out. By the time infantry finally assaulted the position, they would find the bunker intact from the outside, but utterly devastated inside, filled with rubble and casualties. The Allies faced similar situations when attacking German fortifications, particularly along the Atlantic Wall. Hitler had ordered the construction of thousands of concrete bunkers along the coast of France from Norway to Spain, creating what he called Fortress Europe. These weren't just gun emplacements. They were sophisticated military installations with interlocking fields of fire, underground tunnels connecting different positions, and concrete protection designed to withstand naval bombardment. Web. Web Powank. When Allied forces began planning for D-Day, the invasion of Normandy, these bunkers presented a serious problem. Naval gunfire could suppress them temporarily, but even direct hits from battleship guns often failed to destroy them. The concrete was simply too thick, too well reinforced. Bomber Command tried saturation bombing, dropping thousands of tons of explosives on coastal defenses, but the results were mixed at best. Bunkers were small targets, easy to miss, and even near misses often left them operational. Whips. The solution involved a combination of tactics. Specialized armor, particularly Churchill tanks modified to carry massive petard mortars or flamethrowers, were used to attack bunkers at close range. Infantry would use satchel charges and pole charges, essentially large explosive charges on the end of a pole that could be pushed into bunker embrasures or against walls. And yes, bazookas and other shaped charge weapons were used extensively. The Americans in particular found that a team of infantry with bazookas could methodically work their way along a line of bunkers, firing multiple rockets into each position until resistance ceased. Wibiu. But perhaps the most effective weapon against the Atlantic wall bunkers wasn't a shell or a bomb. It was isolation. Once Allied forces broke through the coastal defenses, many bunkers were simply bypassed. Their thick concrete walls, designed to protect the garrison, now became their prison. With no way to retreat and no hope of reinforcement, bunker crews had to choose between staying in place until their supplies ran out or attempting a breakout through hostile territory. Many chose to stay, and some German bunkers continued fighting for days or even weeks after the main invasion force had moved inland, shelling supply routes and harassing Allied operations. Eventually, these positions were reduced by specialized bunker-busting teams using demolitions and flamethrowers. Cheeked. Let's talk about some specific engagements where bunker-busting shells played a decisive role. On the Eastern Front in 1944, Soviet forces were advancing through Eastern Europe, encountering German defensive lines anchored on reinforced concrete bunkers. The Soviets had developed their own concrete-piercing shells for weapons like the 152mm gun howitzer. These shells were designed with thicker walls than standard armor-piercing rounds, allowing them to survive the impact with concrete without breaking apart. Once they penetrated, a substantial bursting charge would detonate, causing massive damage to the interior web. Soviet doctrine emphasized the use of these shells in methodical, deliberate bombardments. Artillery would systematically target bunker complexes, firing repeated salvos of concrete-piercing shells at known fortifications. The goal wasn't necessarily to destroy the bunker with a single hit, but to gradually degrade its combat effectiveness. The first few hits might cause spalling and casualties. Subsequent hits would widen cracks, damage equipment, destroy ventilation systems. Eventually, the position would become untenable, and the defenders would either retreat or be overcome. The Germans responded with increasingly sophisticated bunker designs. Later war fortifications incorporated multiple layers of concrete with air gaps between them. This helped dissipate the energy of penetrating shells. Some bunkers had specially hardened concrete using particular aggregates that were more resistant to penetration. Interior walls were lined with spall protection. Ammunition and critical equipment were stored in separate, heavily protected rooms. But all of these measures added cost and construction time, and by late in the war, Germany simply didn't have the resources to build such elaborate fortifications on a large scale. In the Pacific theater, the Japanese became masters of fortification, particularly in the later stages of the war, when they knew they would be fighting defensive battles on remote islands. On places like Iwo Jima and Okinawa, they constructed incredibly resilient bunkers, many of them carved directly into volcanic rock and reinforced with concrete. These positions could survive bombardment that would destroy conventional fortifications. Naval gunfire that could sink battleships would barely scratch these bunkers. The Americans had to develop specialized tactics for dealing with Japanese bunkers. Often, the only way to neutralize them was to get infantry close enough to attack the entrances directly. Flamethrower teams would approach under covering fire and then blast jets of burning fuel through the bunker's firing ports or ventilation openings. The fire would consume the oxygen inside, making the position uninhabitable. Alternatively, demolition teams would plant large explosive charges directly against bunker walls or doors, using shaped charges when possible to maximize penetration. This was incredibly dangerous work, requiring soldiers to expose themselves to point-blank range of enemy fire. Websites tell you. The bazooka proved invaluable in these situations. A soldier could fire from relative cover, and the shaped charge warhead had a reasonable chance of penetrating even thick concrete. Multiple hits in the same area could create a breach large enough to allow follow-up attacks with grenades or flamethrowers. Intelligence reports from the Pacific Campaign repeatedly mentioned the psychological impact of bazookas on Japanese defenders. They had believed their concrete fortifications were nearly invulnerable, and discovering that American infantry possessed portable weapons capable of penetrating bunker walls was deeply demoralizing. This is a good moment to pause and ask you again to support this channel. If you're finding this deep dive into World War II weapons technology fascinating, please hit that subscribe button and click the notification bell so you don't miss our future videos. We put enormous effort into researching these topics and bringing you accurate, detailed information that you won't find anywhere else. Your likes, comments, and subscriptions genuinely make a difference and help us continue producing this content. Now let's examine the broader technological race that was happening throughout the war. As bunker-boosting weapons became more effective, fortification designs evolved to counter them. This created a classic arms race. Every improvement in offensive capability prompted defensive innovations, which in turn drove further offensive development. One of the most important defensive innovations was the development of high-performance concrete. Engineers discovered that by carefully controlling the mix of cement, aggregate, and reinforcement, they could create concrete that was substantially more resistant to penetration. Ultra-high-density aggregates, special additives to increase hardness, and innovative reinforcement patterns all contributed to improved protection. Some late-war German bunkers used concrete that was nearly twice as strong as standard military-grade concrete from earlier in the war. The problem was that producing this high-performance concrete required specialized materials and careful quality control. In the chaos of total war, with supply lines disrupted and skilled labor in short supply, maintaining consistent concrete quality was extremely difficult. Analysis of captured German bunkers by Allied engineers after the war revealed enormous variation in concrete strength, even within the same fortification. Some sections would be extremely hard and resistant to penetration, while other areas would be relatively weak. Another defensive innovation was the use of multiple separated walls with air gaps. This principle had been used in naval armor for decades. By spacing armor plates apart, you force a penetrator to waste energy breaking through multiple barriers, with its momentum dissipating in the air gaps. The same principle applied to bunkers. A bunker with a thick outer wall, an air gap, and a thick inner wall was much more resistant to penetration than a single wall of equivalent total thickness. Shaped charge jets, in particular, lost effectiveness if they had to bridge air gaps because the jet would begin to break apart and lose coherence. But again, this increased the cost and complexity of construction. It also made bunkers larger and more visible, easier for enemy reconnaissance to spot and target. There's a fundamental tension in fortification design between maximum protection and practicality. The most protective bunker is useless if it takes too long to build or requires so many resources that you can only construct a few of them. Web Eid. Web. On the offensive side, engineers continued to refine penetrating ammunition throughout the war. The Germans experimented with sub-caliber projectiles beyond the Röchling shell, including smaller versions for anti-tank guns. The goal was to achieve the high sectional density of an arrow-like penetrator while improving accuracy. Some designs used discarding sabots, protective sleeves that fell away after leaving the barrel, allowing a small, dense penetrator to be fired from a large caliber gun. These early attempts at kinetic energy penetrators laid the groundwork for modern armor-piercing, fin-stabilized discarding sabot rounds used in contemporary tank guns, or Webbystone, Web-ready Bornstrom. Shaped charge technology advanced rapidly. Early shaped charges had relatively crude conical liners and inefficient explosive fills. By the end of the war, engineers had optimized liner angles, experimented with different metals for the liner, improved the explosives, and refined the initiation systems. The penetration performance of late war-shaped charges was dramatically better than early versions. This drove the development of spaced armor and other countermeasures, creating yet another cycle in the offensive-defensive arms race. Web says, with Bopons, Web Handportreib. One particularly interesting development was the combination of kinetic penetration and shaped charge effects in the same weapon. Some shells were designed with a hard penetrating tip to punch through the initial layer of concrete, followed by a shaped charge that would detonate once inside, creating a jet that would penetrate even further. These compound weapons were complex and expensive, but they offered impressive performance against the most heavily protected targets. Web Hospios. The British, in addition to their massive earthquake bombs, developed specialized concrete-piercing shells for naval guns. The Royal Navy's battleships and cruisers, assigned to bombard coastal fortifications in support of amphibious operations, needed ammunition that could deal with reinforced concrete. Naval concrete-piercing shells were enormous, some weighing over a ton, and were designed to survive the tremendous acceleration of being fired from a naval gun. When these shells hit a bunker, the results were catastrophic. The sheer kinetic energy combined with a large bursting charge could demolish fortifications that would shrug off smaller weapons. Web auf Fien. Wavy Kyogi Mort. There's an interesting psychological aspect to all of this bunker-busting technology that's worth exploring. For soldiers throughout history, fortifications have provided not just physical protection, but also a sense of security and control. A soldier in a bunker isn't exposed to the elements, isn't constantly scanning for threats, can sleep with some assurance of safety. The development of weapons that could penetrate these fortifications had a disproportionate psychological impact. Web Stones, Web 13. Accounts from soldiers who served in bunkers under sustained attack describe a particular kind of stress. Every impact on the exterior sounds like it might be the one that penetrates. You can hear the shells coming, hear the crump of impacts, but you can't see what's happening. You don't know if the bunker is being methodically destroyed, if the next shell will punch through the roof. Some veterans described it as worse than being under fire in the open, because at least in the open you can see the threat and take action. In a bunker, you're passive, helpless, waiting. Web Shatwat, Web Puertost. This psychological vulnerability was recognized by military planners. Bombardment of bunkers wasn't always intended to physically destroy them. Sometimes the goal was simply to demoralize the defenders, to convince them that their fortification couldn't protect them, to induce them to abandon their position or surrender. Intelligence reports from various fronts in World War II noted that fortified positions would sometimes cease fighting after relatively light bombardment with bunker-busting weapons, even when the fortifications themselves remained largely intact. The defenders' will had been broken, Webb thought. Of course, the flip side of this was that soldiers who believed their bunker could withstand enemy fire often fought with extraordinary determination. The defenders of the Maginot Line fortifications that held out until after France had already surrendered, the Japanese garrisons on Pacific Islands who continued fighting in their bunkers until physically overcome, German bunker crews on the Atlantic Wall who kept firing until their ammunition was exhausted all demonstrated that properly designed fortifications could enable small forces to resist much larger enemies, at least temporarily. Webb T. Giroir, Webb, Tuam. Let's look at the technical evolution of concrete-piercing shells in a bit more detail, because the engineering involved is genuinely fascinating. A shell designed to penetrate concrete faces several challenges. First, it must survive being fired. The acceleration inside a gun barrel is tremendous, thousands of times the force of gravity. A shell can experience peak accelerations of 20,000 to 30,000 Gs. Any flaw in the shell's construction, any weakness in the steel, will cause it to fail during firing. Webb. Second, the shell must remain intact during its flight to the target. This might seem obvious, but arrow-like penetrators are aerodynamically complex. They need to be stable in flight, which usually requires fins or some form of stabilization, but fins add drag and reduce velocity, which reduces penetration. Engineers had to balance these competing requirements. Webb. Third, the shell must not break apart on impact with concrete. Concrete is hard, but it's also granular and heterogeneous. When a penetrator strikes concrete at high velocity, it experiences complex forces. The tip might encounter a particularly hard aggregate stone or strike a piece of reinforcing steel. The shell needs to be hard enough to force its way through, but not so brittle that it shatters on impact. Webb. Webb. Finally, if the shell contains an explosive charge, the fuse needs to function properly. This is more complicated than it might seem. The fuse needs to delay detonation until the shell has penetrated through the concrete, not explode on impact with the exterior surface. But the forces experienced during penetration are enormous and chaotic. The shell is being crushed, twisted, decelerated. Designing a fuse that can survive this and still function reliably required sophisticated engineering. Webb. The Germans solved some of these problems with the Rechling shell by making it from chrome vanadium steel, an extremely hard and tough alloy. The long, arrow-like shape distributed the impact forces along the entire length of the penetrator. But as we've discussed, they never solved the accuracy problem. The shell was simply too sensitive to atmospheric conditions. Webb. The British approached the problem differently with their Tallboy and Grand Slam bombs. Rather than trying to achieve penetration purely through hardness and sectional density, they relied on sheer mass and velocity. Drop a heavy enough object from high enough, and it will penetrate through momentum alone. The bombs were designed to remain intact during penetration, not because they were extraordinarily hard, but because they were aerodynamically streamlined and spun rapidly like a bullet. This gyroscopic stability helped them bore straight through concrete without tumbling. Shaped charges, meanwhile, bypassed many of these problems entirely. The charge itself didn't need to penetrate. It could be relatively fragile, because all it needed to do was generate the metal jet. As long as the jet could reach the target before breaking apart, penetration would occur. This made shaped charges much more practical for many applications. A soldier could carry a shaped charge weapon and fire it from short range, something impossible with kinetic penetrators that needed high velocity to be effective. Webbespark, Hochstert, Ponriaverwoistanist, Webampost. The development of the bazooka and similar weapons represented a democratization of bunker-busting capability. Before shaped charges, defeating a fortified position required heavy artillery or aerial bombardment, weapons that had to be carefully coordinated and concentrated. With shaped charge weapons, infantry squads could tackle bunkers on their own initiative. This increased tactical flexibility enormously and reduced the time required to neutralize fortifications, Webb pushed. It's worth noting that not all bunker-busting attempts were successful, and there were some spectacular failures. The assault on the German submarine pens along the French Atlantic coast is a good example. These were among the most heavily fortified structures ever built, with concrete roofs over 15 feet thick. The Germans constructed them specifically to protect their U-boats during construction and refitting. Allied planners recognized that destroying these submarine pens would significantly disrupt German naval operations. Weberos. Bomber Command threw enormous resources at the submarine pens. Thousands of tons of conventional bombs were dropped, including many tallboy bombs. While the attacks destroyed much of the surrounding infrastructure and certainly made life difficult for the German workers, the submarine pens themselves largely survived. The concrete was simply too thick, too well constructed. It wasn't until late in the war, when Grand Slam bombs became available, that real damage was inflicted on these structures, and even then, complete destruction was rarely achieved. Webbo. This highlights an important point. There's no such thing as an impenetrable fortification, but there is such a thing as a fortification that's not worth the effort to destroy. If a bunker is tough enough that defeating it requires more resources than simply bypassing it, then, in a practical sense, the bunker has succeeded in its mission. Some German fortifications fell into this category. They couldn't stop Allied advances, but they could complicate them, delay them, force the allocation of resources that might otherwise be used elsewhere. Webodds. As World War II drew to a close, the technology of bunker busting and fortification had advanced considerably from where it started. Engineers on both sides had learned harsh lessons about what worked and what didn't. Concrete alone wasn't enough. You needed proper reinforcement, spall protection, and redundancy. Kinetic penetrators could achieve impressive penetration, but accuracy was a persistent problem. Shaped charges offered reliable penetration and could be man-portable. But they had limited range and were vulnerable to countermeasures like spaced armor. Massive aerial bombs could destroy almost anything, but they required air superiority and favorable weather. Webwikes, Webarpest, Webhond. The post-war period saw continued development of all these technologies. Modern bunker-busting bombs are sophisticated weapons with advanced guidance systems, allowing them to be placed precisely on target. Contemporary kinetic energy penetrators use depleted uranium or tungsten carbide for maximum sectional density and hardness. Shaped charges have been refined to the point where handheld weapons can defeat thick steel armor, and fortification design has evolved to incorporate all the lessons learned from World War II and subsequent conflicts. Websikas, Web100. But the fundamental dynamic remains the same. The purpose of a fortification is to protect people and equipment. The purpose of bunker-busting weapons is to negate that protection. It's an arms race that has been ongoing for as long as humans have built fortifications, from medieval castles to concrete bunkers to modern underground command centers. Each advance in offensive capability drives innovations in defensive design, and vice versa. For the soldiers of World War II who found themselves in bunkers under attack from penetrating weapons, the experience was terrifying in a very specific way. These men had placed their faith in concrete and steel, in the idea that meters of reinforced concrete could protect them from anything the enemy might do. When that faith was shattered, literally and figuratively, when shells began punching through walls that were supposed to be impenetrable, when shaped charge jets began burning through firing ports, when spalling fragments began ricocheting around interior spaces, the psychological impact was profound. Some soldiers described a feeling of betrayal, as if the bunker itself had turned against them. The same thick walls that were supposed to provide protection now trapped them inside with fragmentation and overpressure. The concrete that spalled became the weapon that harmed them. The very strength of the fortification, its weight and solidity, meant that when it failed catastrophically. The innovation of bunker-busting shells in World War II represented a significant shift in military technology. It demonstrated that no fortification, no matter how impressive, could be considered truly impregnable. It showed that relatively small weapons, properly designed, could defeat massive structures. And it proved that the advantage in warfare constantly shifts between offense and defense, with neither able to maintain permanent superiority. The title of this video refers to secret shells that turned concrete bunkers into burning metal coffins, and we've seen how multiple technologies contributed to this. The Röchling shell, with its ability to penetrate over 4 meters of reinforced concrete, shaped charge weapons that generated hypersonic jets of metal that could burn through walls, massive penetrating bombs that created earthquake effects inside fortifications, concrete-piercing artillery shells that would explode inside bunkers, creating lethal spalling and overpressure. Each of these represented a different approach to the same problem, and each was effective in its own way. The soldiers who developed these weapons were trying to solve a practical military problem. How do you defeat an enemy who is protected by meters of reinforced concrete? The engineers who worked on bunker-busting technology weren't thinking about the human cost, at least not directly. They were focused on the physics of penetration, the chemistry of explosives, the metallurgy of penetrator materials. But the result of their work was weapons that could reach inside fortifications that had previously been considered safe and inflict harm on the people sheltering there. War drives technological innovation in ways that peacetime often doesn't, because the stakes are so high and the resources available are so vast. The bunker-busting technologies developed during World War II represent some of the most sophisticated engineering of the era. They required advances in material science, explosives chemistry, aerodynamics, and fuse technology. They demanded precise manufacturing and quality control, and they incorporated principles of physics that were at the cutting edge of scientific understanding. Today, if you visit the sites of World War II fortifications, you can often still see the evidence of bunker-busting weapons. Concrete walls with neat round holes punched through them, the signature of shaped charge jets, craters from massive bombs that penetrated before exploding, spalling damage on interior surfaces. These physical scars are lasting reminders of the weapons that turned fortresses into death traps. The survivors of bunker attacks carried their own scars. Many suffered from what we would now recognize as post-traumatic stress, the result of enduring prolonged bombardment while trapped in an enclosed concrete space. The helplessness, the inability to fight back, or even see what was happening, the constant fear that the next impact would be the one that penetrated, all of this took a psychological toll that persisted long after the war ended. As we conclude this examination of bunker-busting technology in World War II, it's worth reflecting on what these weapons represent. They're a testament to human ingenuity and engineering capability. They demonstrate how quickly technology can advance under the pressure of war, but they're also a reminder of the destructive capacity that humans can bring to bear against one another, and the lengths to which we'll go to negate each other's defenses. The concrete bunkers of World War II were built to last. Many still stand today, silent monuments to an era of industrial-scale warfare. The shells and bombs that attacked them were designed for a single purpose: to penetrate and destroy. In the collision between these opposing technologies, between fortification and penetration, millions of soldiers found themselves caught in the middle, sheltering in structures that could transform from sanctuaries into tombs in the time it took a shell to impact. Thank you for watching this deep dive into one of the most fascinating and frightening aspects of World War II military technology. If you enjoyed this video, please consider supporting the channel by subscribing and hitting that notification bell. Leave a comment telling us what other topics from World War II you'd like us to explore. There are so many untold stories, so much history that deserves to be remembered and understood. Until next time, thank you for joining us on this journey into the past.